And this section covers both nuclear fission and nuclear fusion, which I mentioned yesterday. Fission is when you split an atom, and fusion is when you put two nuclei together to form a new one. So again, nuclear fission is when a very heavy nucleus splits into more stable nuclei of intermediate mass. This releases tons of energy. This can occur spontaneously, or it can occur when the nuclei are bombarded with particles. Uranium-235 is bombarded with slow neutrons. The nucleus then captures a neutron and becomes unstable. The nucleus splits into a medium mass nuclei with the emission of more neutrons. And the mass of the product is less than the reactants because the missing mass is converted to energy. Now, one of the things that I want to draw your attention to with this, which is leading into the next concept, is that if you bombard it with neutrons, they do a neutron capture, which makes them unstable. But not only does it split into nuclei, but it emits more neutrons. And that is the key, because what you end up getting is something like this, a chain reaction. When fission by neutrons produces more neutrons, a chain reaction can occur because, of course, every step is producing more neutrons, which, of course, will go and bombard more nuclei, making them unstable, and then they release more neutrons. So a chain reaction is one in which the material that starts the reaction is also one of the products and can start another reaction. Every time that U-235 fission occurs, between 2 and 3 neutrons is emitted. So you can imagine that can grow exponentially. The fission continues until all of the U-235 atoms are split, or until the neutrons that are left over fail to strike another atom. If the mass of U-235 is below a minimum, too many neutrons will escape without hitting another, and the chain reaction will stop. So critical mass is the minimum amount of nuclide that provides the number of neutrons needed to sustain a chain reaction. Sometimes you see it in movies, they talk about, well, have we reached critical mass? And this is where a chain reaction starts. Uncontrolled chain reactions provide the explosive energy of atomic bombs, but nuclear reactors use controlled fission chain reactions to produce energy and radioactive nuclides. So I'm sure that you've seen, if not actual videos, but at least like movie recreations through CGI of an atomic bomb being dropped, and you see how much energy that produces. That is for an uncontrolled chain reaction. But for nuclear reactors, we actually control the chain reaction so that we can utilize the energy that's produced. So this is going to explain basically how a nuclear reactor works. Okay, so it's pretty amazing that nuclear power plants, basically the whole idea is that you take radioactive material that heats up water, creates steam, and then the steam powers a turbine generator that creates electricity. That's pretty much as complicated as it gets. So for nuclear power plants, they convert heat made by fission into electrical energy, and there are 5 main components. First, you have the shielding, which you can see, here, the containment structure. 2, you have the fuel, which is here. This is the uranium fuel rod, and you saw him holding one of those little pellets. That's the form that U-235 takes. 3, you have the control rods, which you've got here. I think these are usually carbon. And if I'm not mistaken, the reason why Chernobyl happened is because they used a cheaper material for the control rod. And I think something went wrong with the control rods. 4, you have a moderator. What he was mentioning in the video about how you need a material to slow down the neutrons, otherwise they're just going to fly past the nuclei without hitting them. And in nuclear power plants, we use water. This also happens to act as a coolant as well. And so for number 4 and 5, the moderator and the coolant, this is liquid water for both of those. So the water helps to cool, also produces the steam, but it also helps as a moderator to slow down those neutrons. So for the shielding, it's a radiation absorbing material that's used to decrease the emission of radiation, especially gamma rays from the reactor. Of course, the biggest concern that people always have when it comes to nuclear power is because everyone's afraid of radiation, mostly because of like the weapons that we have made, like the atomic bombs. And of course, you had Chernobyl in the mid 80s. And so people in general are very afraid of the effects of radiation, but that's what the shielding is for. U-235 is the fuel. As I said, it comes in small pellets. And the fission from U-235 produces energy as heat. So that heat needs to be absorbed by a coolant. So here you can see you've got the fuel pellets, which are in these steel casings, and then these are the control rods. So the control rods function by absorbing some of the neutrons so that you limit the number of free neutrons. And this is why I mentioned before about how atomic bombs are uncontrolled chain reactions, but nuclear power plants are controlled chain reactions. So not only are we using a moderator in water to help slow down the neutrons, but we also have the control rods, which help to absorb neutrons so that we don't have too many neutrons making too many nuclei unstable and thus creating an uncontrollable chain reaction. Okay, I've mentioned already that the moderator, which is liquid water, is used to slow down fast neutrons. Nuclear power plants provide competitively priced energy without emitting greenhouse gases or particulates. And this is really important considering there was a new report that just came out, and I haven't had a chance to read it yet, but apparently talking about the effect of global warming and the fact that there are many things which now can no longer be reversed. But again, I got to go back and read the report. I think it's from the IPCC, which I forget what that stands for, but I think Greta Thunberg, she tweeted about it or something. So I will put that on my list to read today. The IPCC is the Intergovernmental Panel on Climate Change. So I can, like I said, they just came out with what they call their 6th assessment report. And if it seems to be easy to read, then I'll go ahead and forward that to you because I'm also interested in reading that as well. But anyway, so this is a really good time to start looking again at building more power plants like this.
So how does a nuclear power plant work? Let's go inside and take a look. Columbia Generating Station is a boiling water reactor that uses nuclear fission to heat water to make steam. We use pellets of uranium, much like this simulated pellet, as fuel. Each pellet contains as much energy as nearly a ton of coal, 149 gallons of oil, or 17,000 cubic feet of natural gas. The pellets are stacked inside fuel rods, and the fuel rods are gathered into fuel assemblies. This model shows how a fuel assembly fits together. The actual assemblies, 764 of them, are nearly 15 feet tall. We put the assemblies, plus 185 control rods and water, inside the reactor vessel. This is called the reactor core. In the control room, a a team of highly skilled reactor operators slowly moves control rods out of the core, starting a chain reaction. The heat produced by the chain reaction is used to boil water and make steam. The entire system is closely monitored and controlled 24 hours a day, 7 days a week. Steam from the reactor vessel is used to turn 4 large turbines, which are attached to a large generator. Together, they turn 1,800 times each minute, producing enough electricity to power a city the size of Seattle. When the steam leaves the turbines, it's turned back to water in a special heat exchanger called the condenser. The condenser has thousands of little pipes just like this one. Each pipe is filled with cool water from the Columbia River. When the hot steam touches the cool pipe, it condenses back to water. The water inside the pipes absorbs a lot of heat, so we have 6 large cooling towers to remove this extra heat. Hot water from the condenser pipes is pumped into large canals at the top of each tower. From here, the water is allowed to fall down across special inserts called cooling tower fill. Large fans pull air across the water, causing the heat to evaporate into the atmosphere. At the bottom of the towers, the cool water is collected and pumped back to the condenser to be used again. Columbia Generating Station produces a tremendous amount of electricity from nuclear fuel. But like any fuel, eventually it begins to run out of energy, so we need to replenish our supply. That's why every 2 years we shut down the reactor for a refueling outage. Right now, I'm standing on the refueling floor directly above the reactor vessel during normal operation, and there's not a whole lot of activity up here. But during the refueling outage, this entire floor is transformed into a strictly controlled and highly choreographed work area. We remove the layers of shielding and various components from inside the reactor vessel, then flood the open cavity with water. Using very detailed procedures, operators move old fuel, called spent fuel, into the spent fuel pool and move new fuel into the reactor. The outage is also an opportunity to do maintenance and upgrades on other equipment that isn't accessible when the plant is operating. It's a busy time for everyone as we move through actions and activities that have been in the planning process for almost 2 years. Our thorough planning and attention to detail help ensure that the work gets done safely and efficiently. This is vitally important to the region so that Columbia Generating Station can be brought back online to provide much needed electricity for another 2-year run. At Columbia Generating Station, we're also taking steps to update our spent fuel storage capacity. After 17 years of use, the spent fuel pool is almost full, so we're building a new storage facility here on site. The Independent Spent Fuel Storage Installation, or ISPSI, uses dry casks to safely store spent fuel until a national repository is built. We're investing millions of dollars to ensure that we'll continue to serve the ratepayers of the Northwest for many years to come. Our nuclear power plant is a shining example of technology and engineering, but the heart and soul of Columbia Generating Station are the people who work here. From reactor operators to engineers, chemists to craft workers, health physics specialists to security officers, each person understands and is committed to their role in keeping the plant running. Human performance is a key element in our success, and we're proud of the many talented individuals who are part of our team.
Okay, I get it. You like your place of work. Okay. Right. So I just wanted, before I play this video, I just wanted to mention there are currently 443 nuclear reactors in operation in 30 different countries around the world. The largest plant under construction as of 2021 is in Finland, and they have the electrical capacity of 1,720 megawatts. And then it says the country with the highest total electric capacity of nuclear reactors under construction is China, where almost 16 gigawatts of nuclear reactors are being built. So basically, nuclear fission technology was approved in 1954, and we've been using it since then. So I just wanted to put that into perspective.
The first explosion blew out the top part of a reactor containment building at the Fukushima No. 1 nuclear power plant. This footage inside the building was taken during a regular inspection. The nuclear reactor is housed behind this robust wall. This is what a nuclear reactor looks like. The uranium inside the fuel rod inside the reactor undergoes nuclear fission. The rods emit heat, generating energy. Usually water cools them to maintain their temperature at 270 degrees Celsius. But if the cooling fails, the temperature could rise to over 1200 degrees. This temperature is hot enough to melt the fuel rods. When the earthquake hit, the first safety system to prevent a meltdown was activated. Control rods rose into the reactor to stop the nuclear fission. As planned, the reactor stopped operating. But the fuel rods were still hot. Water should have been circulated to cool them down. However, this didn't happen because of a power outage right after the quake. So the second safety system turned on. The emergency diesel power generator began spraying the rods with coolant. But an hour later, something unexpected happened. Without warning, the emergency generator stopped. Around this time, a tsunami, possibly as high as 10 meters, hit the power plant. Experts think this is what caused the generator to fail. Now, the third safety system started operating. It converts steam traveling through the pipes into water. It cools the rods, but the water level went down and the temperature continued to rise. All three safety measures had failed. Professor Akira Omoto of the Japan Atomic Energy Commission was involved in construction of the Fukushima plants. He thinks the cooling water somehow leaked from the reactor.
The reactor's coolants must have leaked somewhere in the building. We thought we had taken adequate precautions for a tsunami, but what happened was beyond our expectations.
To forcibly cool the reactor, seawater had to be pumped into it and the containment vessel. Similar failures and a huge explosion also hit another reactor at the plant on Monday. Once again, nature has challenged man's best efforts.
Okay, so that disaster occurred, I can't believe it's already been 10 years, happened in 2011. And as you saw in the video, there were three basic backup plans, I guess, and each one of those failed, which is quite rare.
All of the good we did, it doesn't matter. What does matter is that to them, justice was done. You see, a just world is a sane world. There was nothing sane about Chernobyl.
I'm pleased to report that the situation in Chernobyl is stable. In terms of radiation, I'm told it's the equivalent of a chest X-ray.
You know, Chernobyl is on fire. Every atom of uranium is like a bullet, penetrating everything in its path. Metal, concrete, flesh. Now, Chernobyl holds
Mixture of positive nuclei and negative electrons. And as I've said before, we don't have any material being able to withstand the temperatures required to induce fission. So at the moment, there is no possibility, which is why they start looking into something called cold fusion, which is being able to fuse the nuclei together without this tremendous heat. Scientists can use strong magnetic fields to suspend plasma inside a container, but away from the walls. But large amounts of energy are also needed to initiate fusion reactions. So for fusion to be a practical energy source, more energy must come out than needs to be put in. So it doesn't make sense if they're able to use a magnetic field to contain a small amount of plasma, if it takes more energy to create that magnetic field than the energy you're getting out of the fusion, it's not worth it.
You guys, humanity is another step closer to harnessing the nuclear powers of the sun. Hey guys, Trace here for D-News with some engineering and physics that might change the world. A lot of time we get you on here and we talk to you about those things. They're more conceptual and sometimes really complicated and kind of jargony. But this, oh man, this is juicy. This week, scientists announced that they could produce mini suns. Seriously, for real this time. I know, they've been saying, give us 30 more years and we'll have it. They might have been closer than they thought. We are close to solving the mystery of fusion power that keeps the sun going. While nuclear fission gets a bad rap, nuclear fusion is completely different. It's one of the holy grails of science. Fusion offers a near limitless, pollution-free, cheap source of energy. The deuterium to power the reaction, harnessed from seawater, and its waste is the super rare helium-3 or helium-4, or perhaps more deuterium. Plus, ideally, hundreds of times more energy than we put in. No big deal. The best part? We get all of this with no more radiation than we're exposed to in an average day. Fission involves using heat and pressure to split an isotope of uranium. Fusion involves combining two atoms into one. Both release huge amounts of energy, but the whole fusion thing, so much more efficient. The National Ignition Facility has used 192 laser beams to create an X-ray pocket inside of a 77-ton machine. The pocket superheats the hydrogen deuterium fuel and excites the particles. As hydrogen has a positive charge, atoms normally repel each other. But inside that pocket, as the small piece of fuel burns at 100 million Kelvin, they move so fast they slam into each other, fusing and creating new atoms, releasing massive amounts of energy in the process. This is amazing stuff. While these scientists have confirmed that they can create this reaction for a microsecond, they can't sustain it. And without sustaining it, they won't be able to use it to create electricity. They say we haven't perfected that little pellet of deuterium fuel. It's microscopically uneven, and those imperfections cause it to burn up too quickly. But never mind that. Even though we're not sure how it works, the EU, the US, China, India, South Korea, and Russia are all funding a single fusion plant in France separately from the NIF. It's a different design, but here's to hoping one of them gets this to work, because I could use some cheap, clean energy right about now. So there's one tiny little thing that I probably should point out. Scientists are saying that we are about 30 years from flipping the switch on a power plant, so there's that. But hey, let's be optimistic, right? Guys? Are you on board with this fusion power thing?
Okay. So